Hi everybody, welcome to episode number 2 on my series on Chem 12 topics. Trying to get us through the end of Chemistry 12 here in this COVID-19 stay-at-home. Who knows where this is going. So previous episode I was talking about basic definitions of acids and bases, Arrhenius versus Bronsted-Lowry, how does an acid make a solution acidic, and how does a base make a solution basic. The production of hydronium when you put an acid into water, and the production of hydroxide when you put a base into water, and those basic concepts. Today is going to be about, hopefully fairly straightforward, fairly quick, the equilibrium that water forms just sitting there on its own, nothing added to it. The reason why this is critical is you have to understand water's equilibrium in order to understand, one, what neutral is. Number two, you have to be able to understand what happens to that equilibrium when you add an acid to it, and what happens to that equilibrium when you add a base to that water. And also the foundation of the numerical side of what is pH, what is pOH, the pH scale, more or less acidic, and how acids and bases are working in water. So it's critical to understand water's equilibrium. So that's one of the fundamental things that you have to learn, and that's why I start with it fairly early on when I'm teaching about acids and bases. So today, the equilibrium of water. So last episode, so this is episode 2. Last episode I talked about acids having the ability to donate an H plus to another chemical, and bases having the ability to accept an H plus from another chemical. Well, if you've got a beaker full of water, and that's all it is, it's distilled water, nothing else dissolved in it, then water has only other water molecules to bump into each other. So does anything happen when a water bumps into another water? And the answer was yes. So we have this equilibrium that happens when you've got water. It doesn't matter what the temperature is. If it's pure water, you've got this equilibrium happening. So water bumps into another water, and I should write a little better arrow there. So you've got a water bumps into another water. One of them donates an H to the other one. So one acts as an acid, one acts as a base, forming hydronium ions and hydroxide ions. And when one water bumps into another water, the products are one hydronium, one hydroxide, when they get produced in a 1-to-1 ratio. So no matter how many times that collision occurs, you're always going to get, just from simple stoichiometry and from a ratio perspective, you're always going to get equal numbers of hydronium and hydroxide being produced, always staying the same, if that's all you've got is pure water. So because they're the same, their concentrations will always be the same in pure water, and therefore that's what makes it neutral, is the hydronium, which makes an acid, and the hydroxide, which makes a base. Those values are always equal, and so you end up with a neutral solution. Well, as all things in chemistry are apt to be, that if you've got a forward reaction of water bumping into a water and forming hydronium and hydroxide, that they can turn around and go back the other way. And sure enough, I mean, one's positive, one's negative. Their ions are floating around all over the water. They're actually attracted to each other. So collisions aren't actually so random. So they're actually drawn towards each other. And when they collide, it's quite possible, likely as a matter of fact, that the hydrogen from a hydronium will jump back onto the hydroxide, and it will just turn around and form two water molecules again. So this reaction is quite reversible. So this is typically how we're going to write this equilibrium. Now, we don't typically write water plus water. We just write two waters because you can combine those two. There's two of them. So we'll write two water molecules at equilibrium with a hydronium and a hydroxide. Okay, so 2 water molecules, liquid phase on the left-hand side. That equilibrium, I want to think about this one for a second, think logically for a sec. You're looking at a beaker of water. A beaker of water looks like water. I know that sounds kind of funny, but if you're looking at a beaker of water, it looks like liquid water. And sure enough, that if you look at this, you're not looking at a beaker of water and go, oh my goodness, look at all those ions that are in there. You're not looking at a solidified ionic compound. You're looking at liquid water, which means, kind of gives you some inclination that by far the majority of particles that are floating around in there are liquid water molecules. So this equilibrium strongly favors the reactant side, where the liquid water molecules are, as we're going to see numerically in a sec. I want to go back to the Arrhenius definition I talked about in episode 1, where previously, prior to Bronsted-Lowry knowledge, water might have been considered an Arrhenius form of an acid or a base, and so it dissociated rather than donated an H. So back in the good old days, one might have said, that would be the Arrhenius way of showing what a water molecule does, where it's dissociating. Now, water is a covalently bonded molecule, so it doesn't dissociate. But Arrhenius would have described water as doing what that top equation says. It dissociates to form an H plus ion and an OH minus ion, and it forms an equilibrium. So those ions go back to form water. The reason why I'm showing you that, even though it's not the best way of thinking about the water molecule and how it's creating a neutral solution, is it's not typically, but it's oftentimes used. People will communicate water's equilibrium with just a single water molecule dissociating into H plus and OH minus, even though truly it's 2 water molecules bumping into each other, transfer of an H, and you get hydronium and hydroxide. This equation here is the one that's a little bit more realistic. It actually uses collision theory to explain acidic and basic properties of it. The top one is a little more old school, but again, it's so ingrained into the chemistry world that it's oftentimes used. And so you'll see them interchanged quite often. Don't freak out by it. When you see one, you can think it's just the same thing as the other one. Okay, so whatever is convenient to you, the way that your brain can see it a little bit better, just know that this is more of a Bronsted-Lowry form, and that's more of an Arrhenius form of thinking the same thing. Now, having said that, that's the equilibrium. Okay, so we've already gone with number 1 up there. So what equilibrium? That is the equilibrium. So if you've got a beaker of water just sitting in front of you, you've got water anywhere. Water coming falling out of the sky as rain. That equilibrium is occurring. Anywhere that you have water, you have that equilibrium going. So a teardrop, a puddle of water sitting on the ground in the ocean, anywhere there's liquid water, you have this equilibrium. Now, in the ocean or in your tears or in your blood or in a puddle, you're not talking about distilled water. And so there's other things that kind of mess up the equilibrium a little bit. But if you had pure distilled water, this is all you would have. Okay? But you have to be thinking and kind of keeping in your mind, anywhere that there is water, so any solution that is water-based, has this equilibrium going on with those other things kind of thrown in the mix to mess up the equilibrium. And then we're obviously going to have to get into Le Chatelier. So number 2 up there says, what is Kw? And what is its value? So equilibrium constants. So this obviously is written as an equilibrium. It has an equilibrium constant. So if we if we determine what the K expression is, so the equilibrium expression for this guy. So I'm going to get rid of this one for just a sec. So hopefully we know at this point, Chem 12, that equilibrium constants are calculated by concentration of products over reactants. So we look at this equation, and if I'm going to write down the K expression, then I'm going to write this again just so I have more room on the board. Okay, so if I write the K expression of this equilibrium, KEQ, right? So I'll go back to the equilibrium unit where you wrote the KEQ. So KEQ equals product concentrations. Okay, so I have an aqueous hydronium. So concentration of hydronium. It has a coefficient of 1 in front of it. So it has, in the expression, it has an exponent of 1. So there's a 1 there. I'm not going to write it because I don't need to write it. The hydroxide is the other product. So times the concentration of hydroxide. The hydroxide also has a coefficient of 1, so it has an exponent of 1. So there's our products. Over reactants. But the reactants are in a liquid form. And so because they're in a liquid form and their concentration doesn't change, liquid concentrations do not change, at least not appreciably. So you don't include them in equilibrium K expressions, as you've learned. So there's a 1 down there. So essentially, the KQ of water's equilibrium is just concentration of hydronium times the concentration of hydroxide. And that's all it is. So I'll rewrite this so that it looks nice and neat. Okay. One extra little thing that's in here. This is a very specific, unique equilibrium. It's a super important equilibrium. You'll come across this the rest of your chemistry life. And because it's specific to water and water's equilibrium, it gets a special name. We don't just give it a generic EQ for equilibrium constant. This is called KW, so the equilibrium constant for water. So this is an equilibrium constant. Equilibrium constants, as you've learned in your equilibrium unit, are temperature dependent, which means that if the temperature changes, the equilibrium constant changes because of Le Chatelier shifting. This expression that's here applies, it's a mathematical expression that applies to every temperature. Okay, so I haven't given you the numerical value of KW. I've given you the mathematical expression. The equilibrium constant of water at whatever temperature you're talking about will be whatever the hydronium concentration is times whatever the hydroxide concentration is. So if it's at water at 75 degrees, this expression applies. If it's water at 10 degrees, this expression applies. So if you could, at some kind of weird and wonderful way, you could measure the concentration of hydronium and hydroxide at 75 degrees, you can multiply those two values together and get the value of KW at 75 degrees. Same thing at 10 degrees. If you could determine hydronium and hydroxide concentrations at 10 degrees, you could calculate KW at 10 degrees. Now, typically what is used in a lot of chemistry classes, certainly in Chem 12 as we're going along. I mean, we start talking about different temperatures and things of that nature, but we don't get into great detail on different temperatures. We typically talk about room temperature. In chemistry, that like RTP is room temperature and pressure. Room temperature, under those circumstances, we're talking 25 degrees Celsius. So we, and I think every single teacher in British Columbia would expect you to memorize the value of KW at 25 degrees. I know my students would memorize it. And to be honest, I don't think you even have to try to memorize it. You're going to use it so often that it's just going to stick in your brain. It's unlikely you'll ever get rid of it. It'd probably be frustrating. You're going to be a person my age and still know what it is, and you haven't taken chemistry since grade 12. So what value are we talking about? So through experimentation, the value at 25 degrees has been determined for kW. And so the value of kW at 25 degrees, so kW at 25 degrees So at 25 degrees is 1.0 times 10 to the negative 14. Very small number. What does that tell you? Okay, so if you're thinking back to your equilibrium unit, and probably in the solubility unit, you saw some really small KSPs as well, right? Like 10 to the negative 39 for iron 3 hydroxide. Like numbers that are really, really small. This is a very small number. So what exactly does it mean? Well, when K values were less than 1, that meant that the products, right? So it's products over reactants. The products were really small relative to the reactants. And so if you have a KEQ bigger than 1, that meant that your products were very large compared to your concentration of your reactants. This is a small KEQ. So kW is at 25 degrees. At 25 degrees is 1 times 10 to the negative 14, which means that you're not making, kind of the sense that you're getting here logically, should be that you're not making very many products relative to how many reactants you still have. Which kind of makes sense when you look back at the equation, right? Remember I was saying you're looking at a beaker of water, you're looking at the liquid, you're not looking at a bunch of ions floating around, right? So when you're looking at water, it is dominated by the liquid water molecules, and you can't even see them. Super hard to measure, as a matter of fact. I mean, experimentally determining this value in the first place is difficult to do. So the ion concentrations were really small from a proportion perspective when compared to the water molecules that are floating around. So this value right here is a value that you should memorize, just point blank. Like, go spend 5-10 minutes just saying it to yourself over and over and over and over again. kW at 25 degrees is 1 times 10 to the negative 14. 1 times 10 to the negative 14. Just keep saying it over and over and over again. So what? Like, what does that actually mean? So what it actually means is, if you know that value, if you know the equilibrium expression, can you determine what the hydronium and the hydroxide are in distilled water at 25 degrees? And the answer is yes, using your logic a little bit of mathematical logic, and I guess chemistry logic as well. You know that, okay, going back to the equilibrium, that the hydronium and the hydroxide get made in a 1-to-1 proportion in distilled pure water. So when you've got pure water and you're making hydronium and hydroxide in the same amounts, their concentration will be the same. So when they're at equilibrium and concentrations become constant, they happen to be the same value because they were made in a 1-to-1 ratio. So we know that if you're at equilibrium, so DH2O is just signifying distilled water. So distilled water at equilibrium, distilled water, not anything mixed in, it's just pure water, that's all you have. The hydronium concentration equals the hydroxide concentration, and that's why water is neutral, because the two of them were equal to each other. So the numerical value of those two things has to be the same. Okay, makes sense. So if those two things have to be the same, and those two multiplied together give you kW, then 1.0 times 10 to the negative 14 should equal, and if I say those two concentrations, I'll throw in a math variable, x, and say you don't know what they are, but they're the same, they're both x. Well, this then would be x times x, or x squared. So 1.0 times 10 to the negative 14, the value of kW at 25 degrees, equals x squared. So obviously the square root of 1 times 10 to the negative 14 is x, which would be the concentration of the hydronium and the concentration of the hydroxide when you're talking about distilled water at 25 degrees. So, having said that, when you're taking a little side issue here, when you're doing things mathematically, if you take the square root of the number in the scientific notation, like if you can do it, like square root of 1 is 1. So the answer to this is going to be, if you've got 1 times 10 to the negative 14, the square root of 1 is 1. If that happened to be 9 times 10 to the negative 14, the square root of 9 is 3. So the square root of 1 is 1. And then you just have to figure out the times 10 part. And when it's an even number, and you're taking the square root, then you just divide it by 2. So if it's 10 to the negative 14 and you're square rooting that, it's 10 to the negative 7. It stays negative, and it's half of 14 is 7. So 10 to the negative 7. Now it's molar. So the concentration of these guys is in molarity, as KEQs are. So X, forget X, let's put in hydronium and hydroxide. They are both 1.0 times 10 to the negative 7 molar. That is at 25 degrees Celsius. Okay, so when the temperature is not 25 degrees Celsius, it's something different. But we can say that right now. Now, we're talking distilled pure water at 25 degrees. And it's neutral because it's distilled water. So hydronium equals hydroxide. What have you learned about the pH? Let's go back to, I don't even know when you first learned this, neutral on the acid-base scale. So on the pH scale. What is neutral? Well, you learned neutral was 7. Well, at 25 degrees, pH is 7 when it's neutral. Well, where do you see a 7 up there? So we're not going into this yet, but yes, the concentration of hydronium and hydroxide has to do with the pH and pOH of a solution. That's where the logarithms are going to come in. So we'll deal with that. That'll be in next classes. You can actually see, and we're going to be talking about that stuff later. The third thing is the Le Chatelier effect of acid and base. So you've got this equilibrium, and so we're going to combine acid-base, we're going to combine water equilibrium, and we're going to combine Le Chatelier effects. So, Le Chatelier effects. I guess I didn't really need to erase my water equilibrium. So let's go back to this. Okay, so if we have, there's your basic water equilibrium. So if I have water equilibrium, and let's start with an acid, and the same thing happens with the base, it's opposite, but we'll go through both. The base I'll go through really quickly. So when I add an acid, what does the acid do? So imagine for a second you've got a beaker of water sitting in front of you, just a big giant beaker. It's water, pure water. It's at 25 degrees, who cares? It's just sitting there. And you take some acid and you drop it in. Who cares what the acid is? It doesn't matter. You take the acid and throw it into the water. You dissolve it in the water. So what exactly happens? So a generic acid, we oftentimes write it as HA. So I'll write it in a different color. So I'll do it in red. So HA is the acid. I add it into water. And because it's an acid, it donates its H to water and forms hydronium. And then the acid, the HA, lost its H, so it's now down to A, and its charge has gone down to a -1, because it was neutral, it's now down to -1. Whatever A was. Could be chloride, could be sulfate, it could be a bunch of things that acids are made out of. So this is generic, so who cares what A- is? Doesn't matter. The critical part here, though, is that when you add an acid, you kind of think of it kind of over on the side, doing its side business over here, and the HA donates an H onto water, and that water then becomes hydronium. So, I mean, relatively speaking, you're not talking a ton of it relative to how many water molecules are in there, but enough that the hydronium now is bigger than it was previously. Okay, so the acid's effect is to make more hydronium than was in the water before. Now, that extra acid, right, that extra hydronium, I should say, that hydronium that gets made then goes over to the water equilibrium. So almost think of the acid making the hydronium over here on the side, and it produces hydronium. Well, that hydronium now goes over to the water equilibrium that's happening everywhere and messes it up. So in Le Chatelier, anytime you increase the concentration of something, then there's a Le Chatelier shift to deal with that stress. So when you increase concentration, things shift away from where that component was to get rid of it. So if I go with my blue pen here, and here's my hydronium in the water equilibrium, if the hydronium made by the acid then goes over to the water equilibrium and says, okay, let's spike this guy up. Right, let's increase that concentration. Well, then think of it like 2 barrels of water connected by a tube. If you've lifted this guy, water's going to pour over that away. So if I've lifted this guy up, it's going to pour that away. And by pour, I mean chemically react the other direction. So that's how chemical systems, Le Chatelier, shift. They get rid of things by chemically reacting them away. And so the hydronium that was over here reacts with some of the hydroxide. It goes this way to form new water molecules, and as an effect, those concentrations start to go down a bit during the shift to try and get back to that equilibrium constant. So they multiply together to give you Kw again. So that Le Chatelier shift is kind of critical because, and let's show this graphically, this is where it's going to get really interesting. So you've seen these Le Chatelier graphs before when you're doing your equilibrium. And if I have on here, if I graph the hydronium concentration, not sure I've got that flat, but that's flat. Pretend that's horizontal. And the hydroxide. They're on top of each other because they're the same value. So before I added the acid, the things at equilibrium, hydronium and hydroxide and distilled water are the same value. And not only that, it's 1 times 10 to the -7. So at this point right here, and I'll put a little dotted line. At that point right there, that's when we added the acid. So when we added the acid, and it went over to the water equilibrium, and it messed it up, okay, with a spike in the hydronium concentration. How do we show that graphically? Okay, so your brain has to see 2 lines here. There's actually 2 lines on top of each other. The hydronium and the hydroxide are on top of each other, but there's 2 lines there. So we got a spike up of the hydronium. Okay, so the spike up is increased hydronium concentration because the acid made it, and so up it goes. We didn't touch the hydroxide, so the hydroxide is still right at that level right there. So it's right at the end of this horizontal line. The H3O plus is now up here because of the stress that was created. Then there's a Le Chatelier shift. And during the shift, everything goes that way. Not only do they go from right to left, that means they're going down, but it also means they're going down equal amounts. So if this guy drops and then reestablishes equilibrium, so the hydronium goes down, during the shift, the amount it goes down will be exactly the same as the hydroxide. So this drop right here and that drop right there, so how the hydronium goes down and how the hydroxide goes down during the shift, they have to be the same amount because it's a 1-to-1 ratio. These are in a 1-to-1 ratio, so this drop here, call it X, and that drop there has to be the same amount. So went through that pretty quickly because I'm hoping that you've all done Le Chatelier before and these graphs don't look completely foreign to you. What is critical though, okay, I guess there's a lot of things going on here, but what is critical is before we added the acid, right here, the hydronium and the hydroxide were the same concentration. Therefore the solution, pure water, was neutral. We added the acid. The hydronium spiked up. There was a Le Chatelier shift in water's equilibrium. We no longer have the hydronium equaling the hydroxide. As a matter of fact, we have hydronium being larger than the hydroxide concentration. Now, those values that they're there, this is just a qualitative thing. Don't kind of quote me on what the actual numbers are. Doesn't work out quite that easily on this graph. This is just to show visually that the hydronium and the hydroxide are changing in concentration because of a Le Chatelier shift in water's equilibrium. The stress was caused by the addition of the acid. And once you've added the acid, hydronium is greater than the hydroxide. Now, having said all of that, what would it have looked like if instead of adding an acid, I added a base? Well, the product of a base is what it does is it rips an H off of water and it produces hydroxide. So the graph would have looked exactly the same, like the plateau before would have looked exactly the same. The spike up would have looked exactly the same. The curving down and the shifting of both lines would have looked the same. What would have been different is this one would have been hydroxide rather than hydronium. This one would have been hydronium rather than hydroxide, which means that this would have been the other way around. The hydroxide would have been greater than the hydronium, not balanced anymore. So acids make the hydronium outweigh the hydroxide. Bases make the hydroxide outweigh the hydronium. You can think mathematically too that Kw, being 1 times 10 to the negative 14, is constant. That's why it's called an equilibrium constant. So as long as the temperature stayed the same, those two values, wherever these two plateaus finished numerically, they would have still had to multiply to 1 times 10 to the negative 14. And that concept is where the mathematical part of all of this comes in. and that's going to be next class. So I'll see you next time. We'll be talking about all of that, and we'll get into logarithms and what pH truly is, what POH truly is, and all the mathematical relationships that come in. So if this has been helpful, that's great. Next one I'll do as soon as possible, and if you subscribe to the channel, then obviously you'll just see the videos in the series. So my intention is to just keep going till the end of the year, and you can learn as you're going. Great. I'll see you later.